All right, last couple slides on this set of notes. There's actually a continuum of bond types, so that means it's not just a jump from one bond type to another. We start at one extreme, which is pure covalent nonpolar. So pure nonpolar covalent bonds, those are bonds that there is absolutely zero difference in their electronegativity. And then on the other extreme is a very strong ionic bond where there's a huge difference in electronegativity, something like 3.3, going from 0.0 to 3.3. If it's between 0.0 and 0.4, we call that a covalent bond, a pure covalent bond, or nonpolar. If it's between 0.4 and 2.0, in general, as a rule of thumb, we call that a polar covalent bond. And if it's between 2.0 and 3.3, we generally call that an ionic bond. And you've got that mentioned over here in this table. We've got small, intermediate, and large differences in electronegativity, ranging from covalent or nonpolar covalent all the way over to ionic. When two electrical charges of opposite sign are separated by a distance, a dipole is established. You could think of a magnet as a dipole. It's anything that's got one end that is positive, the other end that's negative, and there's a little bit of distance between the two ends. The quantitative measure of magnitude. Oh, and by the way, any molecule is going to be is going to have a dipole in it. The quantitative measure of the magnitude of the dipole is called dipole moment. Let me take that back. A molecule that is not nonpolar. The only ones that don't have a dipole are nonpolar. We'll get to that in a second. The quantitative measure of the magnitude of a dipole is called its dipole moment. So in other words, how strong of a difference, how great of a difference in charge over that distance do we have? That's called your dipole moment, and the units are debye. If a molecule is nonpolar, it has a dipole moment of 0 because there's no difference in electronegativity. You've got an example right down here. The chlorine molecule has 0 difference in electronegativity, so its dipole moment is 0. Assuming that the bond lengths are pretty similar, as the electronegativity difference between two atoms increases, the dipole moment of the bond between them also increases. So if the electronegativity difference increases, the dipole moment also increases. So it makes sense, as you look at what we have down here, as the electronegativity increases, the dipole moment also increases. The strength of that dipole. Let's do a couple examples. SnCl4 is a colorless liquid at room temperature. It freezes at negative 33 degrees Celsius and it boils at 114 degrees Celsius. Do these properties suggest that it's ionic or covalent? Do we have ionic or covalent bonding in the substance? Think about it for a little bit. Okay, so I'm noticing the freezing point is negative 33. Let's compare that to another substance we know the freezing point of. I know the freezing point of water is 0 degrees Celsius. So it's actually a lower freezing point, or you could say a lower melting point than water, which means it's easier to break the bonds in this substance, to melt it, than it is to melt water. So that sounds like it's probably going to be covalent, but let's go through it step by step. You compare it to water. Water has a melting point of 0 degrees Celsius and a boiling point of 100 degrees Celsius. So the melting point and boiling point of tin chloride, SnCl4, are similar to water. The low melting point, which is lower than water, and low boiling point, which is almost as low as water, indicates that the attractive forces between the units are relatively weak, because it seems like it's pretty easy to break if we only need to get it up to a temperature of negative 33 degrees Celsius for it to melt. The forces broken must be IMFs, because they're easier to break than ionic bonds. They're actually, on one end of it, it looks like it's easier to break than even water, so that indicates it must not be a stronger bond, a stronger intermolecular force, so it's probably a covalent compound. All right, let's do another example. On the basis of the information on the table, we want to arrange CCl4, H2S, CS2, and SiF4 in order of increasing bond polarity. I don't know why I have a question mark there. All right, keep in mind, bond polarity is not the same thing as molecular polarity. For any of you who are thinking back to last year when you really had to know the shape of the molecule to tell if it was polar or not, we're not getting into that yet. We'll talk about that later. Right now, we're just looking at whether the bond itself is polar. So we're just comparing the two different atoms. How polar would that bond be? So in CCl4, I just want to compare carbon and chlorine. So carbon has an electronegativity of 2.5 and chlorine has an electronegativity of 3.0. I want to know the electronegativity difference. In the CCl bond, the electronegativity difference is 3.0 minus 2.5, which is 0.5. In H2S, I'm going to be comparing hydrogen and sulfur. So 2.5 minus 2.1, that gives us 0.4. In CS2, I want to compare carbon, again 2.5, to sulfur. Well, sulfur is 2.5. So 2.5 minus 2.5 is just 0. SiF4, I'm comparing silicon and fluorine. 4.0 minus 1.8 gives me 2.2. So now I could arrange these in order of their polarity. The most polar is going to be SiF2. It's my biggest number, and the smallest number is 0. So CS2, which is the one that is 0, is the smallest difference in electronegativity. So it's going to have the smallest dipole. And the largest is SiF4. That works out well. It kind of makes sense. These two are actually nonpolar covalent because they're less than 0.4. They're 0.4 or less as an electronegativity difference. And if you look at the bond in CCl4, it has a 0.5, a difference of 0.5. Remember, that difference of 0.5 is considered polar covalent, and the difference of 2.2 is considered an ionic bond. So that's kind of where those words at the bottom come from. All right, that's it for types of bonds. You've got a simulation and some practice to work through after you're done with your notes.